Hello, my name is Felix. Our topic is comparing QUIC and HTTP 3 implementations. Before we start, let me thank Dr. Penn. He encourages me to make a better presentation than the original authors. By the way, the authors presented the idea to the network research community, in which many concepts could be well known. I'm doing the presentation differently, although my presentation skills are not as good as the authors. I fill in the fundamental ideas before going into details, and I will also introduce view angles from other contributors in the community. I want to clarify that this topic is quite new to me as well, and please feel alright to correct me if I am wrong. To begin with, let's start the story by web browsing. According to a Google TED Talk, most websites reserved on the internet were single static pages containing one resource hosted by one domain in 1990. By 2014, most websites with browse became 1.2 megabyte pages containing 80 resources distributed in 30 hosts. To fulfill a better user experience for web browsing, the researchers found the protocol layers were not efficient enough, and in 1988, the initial proposal of QUIC was formed. The full name of QUIC is QUIC UDP Internet Connections. The main idea was to create another internet protocol or layers of protocols to replace the existing protocol stack and improve web browsing. Its design was to transform HTTP, TLS, and TCP into HTTP2 and QUIC. In my view, QUIC and HTTP3 improved HTTP by handling internet connections on the application layer instead of doing so on both HTTP and TCP. In other words, this improvement on an internet protocol is another instantiation of end-to-end arguments. At that time, Google developers identified several issues that led to latency in web browsing. One of them was about the number of handshakes made in the protocols on different layers. This includes TLS and TCP. In terms of establishing connections, when sending HTTP requests over TLS, web browsers established 3 handshakes to the web servers. The first handshake is for TCP connection, and the second and third handshakes are for the TLS protocol. This problem was more apparent when traffic went through the Atlantic Ocean, where one round-trip time for going back and forth the ocean was around 100 milliseconds. Therefore, QUIC will give a token to web browsers the first time they connect to web servers, so that one handshake is required in subsequent connections. This is called 1RTT. Also, if the web browsers start their HTTP request and establish the connection simultaneously, they further reduce the delay between establishing the connections and the commence of data transfer. This is called 0RTT. Traditionally, as each TCP connection connects only one stream, if web browsers send one request for one resource at a time and send another after receiving the resource, the clients kept waiting for responses. The server also had to wait for the subsequent request. Therefore, the bandwidth would have been unutilized. A simple fix to this problem was to establish multiple connections to different hosts. When our browsers wanted to retrieve various resources all at once to reduce the wait time and enhance user experiences. However, this fix may not be as efficient as we may think. For example, if we increase the number of connections from 6 to 10, we know the performance will drop due to the imposed overhead. Now, QUIC tries to tackle the problem by multiplexing. The multiplexing combines streams into one single stream before sending data into the connection, and demultiplexes them back into to the corresponding streams when received at the other end. This scheme allows multiple streams to enter and leave one TCP connection. Around the same time, another protocol, SPDY, also served the purpose of stream multiplexing. Though SPDY was not necessarily sitting on top of TCP, their implementation encountered the head-of-line blocking issue. Suppose web servers did not acknowledge data retrieval, nor did the web browsers retrieve the acknowledgement. In that case, the retransmission of a packet for one particular stream would block transmissions of all other streams. It was also the reason for QUIC to implement its retransmission and scheduling mechanism. QUIC and HTTP2 did not come with great success because at the very last moment, when HTTP2 went through deployment, the developers were still adding the per-stream controls on the multiplexing to the protocol. The system was to control how bandwidth was distributed across concurrent web page resource channels, and it was complicated. What's more, this system was poorly tested, and 5 years after the protocol standardization, when the HTTP2 web servers and web browsers do not correctly support this feature. Finally, researchers decided to redesign this system entirely to have HTTP 3. Back in 2016, the researchers standardized QUIC, and in 2017, Google thought they demonstrate great success in their implementation. They showed an increase in throughput, a drop in search latency, and a decrease in video rebuffer. However, other contributors have not yet started their implementation at that time. They were trying to pick up and did their implementation according to the specification. In 2020, Facebook also found QUIC reduced request error, tail latency, and mean time between rebuffering. Unfortunately, in the same year, Cloudflare found HTTP 3's performance was even worse than HTTP 2, owing to the differences in congestion control algorithms applied in TCP and QUIC. Meanwhile, independent researchers in academics even point out that QUIC performed worse for all network conditions in a local environment. These results was mainly due to unoptimized open source libraries. Others also said QUIC performed better for small payloads, but worse for large payloads upon packet loss. These results was caused by their congestion control, apart from the unoptimized open source libraries. In 2021, Alexandra mentioned the conflict in results could be the consequences that researchers in the industry largely optimize their environment in production. Conversely, those from the academics conduct their experiment in their unoptimized environment. Concerning the study comparing TCP's and QUIC's performance, Conrad found that all previous work compares an unoptimized TCP with a highly tuned QUIC web stack. So what is the truth? Robin thought that although researchers have proposed QUIC and HTTP 3 by combining lessons learned from TCP and HTTP 2, they have not fully grasped the actual behaviors of the QUIC protocol. In 2020, as Robin pointed out, researchers mainly tested the new protocols on compatibility, but bugs still came out because the tests were not rigorous enough. For those features, the specification did not stay. The design was up to the choice of developers. An existing test did not cover those optional ones. Most of the academic work evaluating this protocol was not updated accordingly as the development progressed. Also, the previous analysis on QUIC is full of human bias. In 2018, the authors proposed in their previous work both qlog and qvis, which are the log format for writing log files on endpoints, and open-source online tool suite for interactive visualization of qlog correspondingly. Since the QUIC community adopted qlog widely, the authors in this work used both qlog and qvis to assess the maturity of 15 out of 18 active implementations of QUIC and HTTP 3. Correctness is one concern. Quality of experience is another. Since Google, Facebook, and Cloudflare were hosting production endpoints in 2021, Alexandra also conducted one of the first studies on comparing the performance of QUIC and TCP on these production web servers on various aspects, such as network conditions, weather, and client implementations. They also realized the importance of testing these protocols and thus built a tool to systematically analyze the root causes of performance differences between protocols and make new observations. They also applied Chrome netlog and pcap along with qlog and developed their visualization tools. Netlog was a tool to capture traffic on the application layer, while pcap was another tool to record traffic on layers at lower level. Talking about the measurement, Alexandra used a multi-object measurement tool to correlate high-level quality of experience matrices such as speed index and page load time. Here comes the results. The flow control in TCP is to provide a receive window on receiver size and tell sender size to send more. This control is to avoid stalling. We have three kinds of approaches to this flow control problem. One of them, the static approach, keeps the receive windows unchanged, while the second, the dynamic approach, is to double the windows when stalling occurs. The third one is the auto-tune between two modes. Although the third approach is well known in TCP, most QUIC implementations simply follow the first approach because the developers just wanted to play safely without attempting to fine-tune QUIC. Therefore, as shown in the graph, the bytes in flight did not pick up even the receive windows increases. We also see that the QUIC development is not as fast as the TCP one. The congestion control contributes much to the performance of QUIC, so this adaptation was also of the utmost concern. As of 2020, the TCP congestion control is going through a significant evolution, while the QUIC congestion control is in both implementations still sticks to the old new window. Although QUIC could purely run its own congestion control, it could also adapt to TCP and take advantage of the TCP advancement. Moreover, developers did not treat the congestion control in most QUIC implementations. For example, initial congestion windows determine bandwidth utilization at the risk of early packet loss. Another one is pacing. Instead of sending packets in bursts, the pacing was to send the packets steadily into the connection at a data rate equal to the throughput. Though Google developers in 2014 did implement them, so some implementation did not tune the initial congestion windows or perform the pacing. Another chief idea for QUIC was zero RTT. Due to the security, web servers did not return data 3 times larger than those requests browsers sent, at least on the first connection. This ratio is called the amplification limit. Servers could grant address tokens to trust clients, and from the second connection onward, the server could ignore this limit if clients shows these tokens. However, in some implementations, it was found that developers did not follow the address token design. Some also simply allow a large amplification limit or ignore the limit in some particular cases. Multiplexing was one of the most important ideas when QUIC was first proposed. There are also three primary source schemes. When there are multiple streams, the sequential strategy means QUIC send the stream one after another. The round-robin approach means QUIC switches between streams when it sends them. The third approach allows per-stream selection on whether they are sent sequentially or in round-robin way. As shown in the table, only 5 out of 13 implementations have adapted the third approach. As we have come across in previous slides, leaving this feature in late development was the cause of HTTP 2's design failure. If we have learned a lesson, why do we still do the same things as before? To some, concerning the QUIC, some QUIC implementations did not follow all the standardized features, unoptimized, and buggy. However, QUIC is just one angle we viewed on software development, and so far, we have not looked at the head-of-line blocking, which allows more content to load even when one of the streams is blocked. So what are the actual user experiences this new protocol gives us? And how to measure the user experiences when it comes to web browsing, especially when loading multiple resources? One of them is about speed. The speed index calculates what percent of the page is visually complete at every interval until the page is visually complete. The figure on the left shows the speed index on different QUIC implementations under various network conditions. The numbers displayed on the boxes show the percentage increase in speed index compared to TCP. The boxes colored in blue means HTTP3's implementations perform better than HTTP2's ones. The figure on the right shows under different network conditions, the start time and the end time web pages are being loaded. It is observed that web browsers may start to load web pages later when compared to TCP. Web browsers may finish loading web pages earlier though. That's why we can look at the page load time apart from the speed index. HTTP3 loads images earlier when compared to HTTP2. It is found that resource load order doesn't impact page load time as much as speed index. Still, the page load time results match the speed index results. The figure shows that HTTP3 has a slight advantage over HTTP2 for small web pages, but no clear benefit for bigger web pages. Their graphical results are more interesting in the way that they show HTTP3 is again better than or equivalent to HTTP2 during extra packet loss. To conclude, we will have a better web browsing experience in the foreseeable future after a complete testing is done. That's all. Thank you for attending my presentation.